All right, we have the electric field, so we're going to start with a bit of review. We're going to talk about the gravitational field in general and Coulomb's law from yesterday. Then we're going to talk about the electric field in particular. And we're going to introduce the test charge and a point charge into that. And we'll finish with the superposition principle. And then we'll get into the electric field for, in fact, I should have put that above the line, the electric field for objects of continuous charge. Okay, and that's where we'll finish for today. Newton's law of gravity, so his gravitational law was force of gravity equaled the gravitational constant times the mass of a big object times the mass of a little object, usually r squared. Okay, and for this to be a vector, we needed to have the r hat in here. And because it's always attractive, we assign that to be a negative r hat for gravity. And this would equal mg, which is a vector. Now, if we are close to the Earth, if we are an object that is close to the Earth, this g remains the same pretty much wherever you are. But that's just because you are at pretty close to a constant radius from the center of mass of the Earth, and so your acceleration due to gravity is going to change. However, this g can also take on a different idea. So, for example, if you are holding an object within Earth's gravitational field, you may feel its weight. Okay, but it's not necessarily accelerating. And so what you are feeling is the effect of the gravitational field of the Earth. And so what we get for this g is also known as the field strength. This g can change as your radius changes from the Earth. Okay, if you go further out, g might drop down to 7.6, depending on how far you are from the center of the Earth. And that in that particular place, that gives you the field strength in terms of newtons per kilogram. That if you have a certain mass that's held a certain distance away, that you're going to in this field, you're going to experience so many newtons for every kilogram of mass. And that's how we describe gravitational field. Okay, now yes, the units of this g are in meters per second squared, but we can also treat it as newtons per kilogram, okay, when we're talking about the field. So the similar thing happens when we deal with the force of electricity, or of an electric field, where we have our Coulomb constant times a charge that we're going to be examining. All right, and we'll call this a Q naught down here. This is going to be our test charge, and it is usually a very small amount of charge, so it doesn't affect stuff around it, and it is always positive. So when we talk about a test charges are always positive. And this would be divided by the square of the distance between them, and we throw in our r hat for our direction. All right, this leads us to, if we follow the same analogy that we have up here for the gravity, this is going to give us our electric field. Okay, and our field is going to be based on our charge. So our electric field is equal to, okay, and it's analogous to g. All right, and that's why we covered this. Our electric field, the strength of our electric field, is analogous to the g, the acceleration due to gravity. And this time it's just going to be the force due to the per unit charge. And if we divide both sides by our test charge, okay, we would get our we get this. So our electric field is defined as the force of, the electrical force divided by the test charge, the charge on the test charge that's around it. Okay, and these have units of newtons per coulomb based on your test charge. Okay, and so what does this really mean? Well, this gives us our E, or another way of writing this is our force is equal to our test charge times our electric field. Is another way of doing it. Time the electric field at any particular point. But this can be a little complicated, and this will often be a function of your radius. Okay, from where you are in space around your charged particle. All right, so our electric field is also going to be Q naught over R squared R hat, all of that divided by Q naught, which is what we did over here. And that gives us an E, which is equal to KQ over R squared R hat. Okay, where this is the Coulomb constant, this is the charge that is generating the electric field. Okay, this is the radius that a test charge would be from the source of that electric field, and that's our vector R hat. Okay, so let's say that we have an object over here. We'll call this Q1. Let me shrink this up a little bit. This will be Q1. And we have another one over here, Q2, another one over here, which is Q3. And then somewhere in space around it, we have oh, that's not on the screen. Okay, so let's rotate over. And somewhere over here, we have Q naught. All right, and so our force from Q1, let's say they're like charges, and so Q1 is going to give us a force that is, in that direction, and Q2 will give us a force that is in that direction, and Q3 is going to give us a force that's off in, or let's say this is an attractive one here, and so it would be in that direction, and this is going to be, this is the force due to number 2, and this is going to be the force due to 1, and this is going to be the force due to 3. And this gives us our superposition principle. Okay, so these would be our point charges, by the way. 1, 2, and 3 would be our point charges, and Q naught is our test charge. Okay, and the superposition principle just says that you can add them all up. Okay, but it has to be according to vector addition. So, F2 is going to have an X force and a Y force, and this one's going to have an X force and an itty bitty Y force, and this one's going to have a Y force and X force, and so you just add them. We do the vector addition for all three of these, and that's how we're going to get the total electric field strength for this particle at that point. Yeah? Okay. Well, you guys probably see what's coming, that if we just add them all together, that means that we're going to be getting an electric field that's going to equal, if we're adding them all up, then we're going to have I equals 1 to n, okay, of all of our charges, r squared, ri squared times ri hat. And this winds up being, okay, the summation, the superposition principle for all of these winds up being the summation notation, which of course means whenever you see summation notation, we just add them all up. This leads us into an integral, right? Okay, anytime we have the summation notation. So imagine that instead of just being point charges, we have a blob. And it is evenly distributed. This whole thing has this even charge distribution throughout. Now, there's point charges everywhere throughout our object. And right in here, I'm sorry, and we have a point outside of this. This point right here is going to be our test charge, Q naught. And this right here is our differential amount of charge, dQ. So this right here, okay, is our R. Okay, so the distance from our differential charge. It could be whatever distance it is, because it depends on the value of the charge. Or the distance doesn't depend on the value of charge, but the direction of the force will. And that means that this right here, our summation notation, instead of being summation, it leads to our integral of our continuous charge. Okay, and so our electric field is equal to the integral of our Coulomb constant over R squared dq r hat. Now, it looks all fine and dandy. The problem is Q and R need to be of the same variable. And so how did we do that? We've seen this before. Okay. Yes, we've seen this before when we're dealing with center of mass and find out where that is. So we now need to determine how dq and r are going to relate to each other. So just as we had mass density before, we now have charge density. All right, so if we have a linear, yes, the uneasy laughter of remembering our mass density. Okay, so if we have a linear situation, okay, we use actually the same variable for the density because it's a user assigned variable. Our linear charge density is going to be lambda. Okay, lambda is going to equal our amount of charge for a unit length. Okay, and the units of this is going to be Coulomb per meter, or C per M. Okay, and and so if this is C per M, then our dq, okay, is then going to equal our lambda times our dr. Okay, and all of a sudden we can take this and plug this back into here, and now we have something that's in terms of a variable r and whatever our lambda value is. Okay, and that we can integrate. Okay, we can, okay, and the other two apply right along with, and so we also have, okay, let's slide that up a little bit. Okay, we've got an area, then our area now is, it goes on that way and that way. Okay, and it also has a uniform charge throughout. We will find that we need, according to our math, we need to have uniform charge. We are not prepared yet, some of you may be, but we are not yet prepared to handle an ununiform charge. Okay, even if it might change, the charge might change over the space of your object, but it would be a continuous change. So it would with that we can handle, that kind of math we can handle, but just not differing charge densities. What's that? Right, that is not good. We don't have the math for that. All right. So if we have an area, then this of course becomes sigma, because that was our unit for sigma charge density. For area density, and that's area over charge. Okay, and this would give us a dq equals sigma dA, and this can get a little tricky because we have to define this according to we have to find a common variable between our radius and our area, and if we're dealing with multiple dimensions, that can get a little tricky. And also finally, we have volume, which is okay. So if we have a sphere with a uniform charge on it, okay, and then we deal with rho as our charge density. And so our dq then equals rho dV for our volume. And that is that. So, right, so that's our continuous charge. It's effective electric field and how to calculate electric field based on our continuous charge.